So we just talked about refraction. We want to talk more, go a little deeper into special cases of refraction. So again, if you have a ray of light coming from a high index of refraction to a low index of refraction, what is it going to do? First, you draw your normal line. You draw your path of no refraction, no bending, straight on through, and then you say, is it going to bend away or towards the normal line? In this case, it's going to bend towards the normal line. Okay, but you also have a reflected ray that obeys the law of reflection. Okay. Second scenario, if you go from a high index of refraction to a low index of refraction, what is it going to do? First, draw our normal line perpendicular to surface and no refraction ray, so straight on through. Is it going to bend away or towards? In this case, it's going to bend away from the normal line. And then we also have a reflected ray that obeys the law of reflection. Okay? So, what happens if we increase the angle of incidence? What happens to the angle of refraction? So, what what we see is this. So, we're increasing the angle of incidence, and what's going to happen? The angle of refraction is also going to increase. It's going to bend more away from the normal line, and our reflected ray still obeys the law of reflection. Let's do it again. What happens if the angle of incident angle is increased? The angle of refraction is also increased. And we're like, oh man, what's going to happen? And so, angle of reflection, again, we can increase it even more. Like, what are we doing? What happens? Like, whoa, that's crazy. It bends away more, even more from the normal line. And we still get our angle of reflection. But now what? Like we can't bend anymore. What we get, we now have total internal reflection. None of that got out. So a critical angle, what is that? That is the angle of incidence that causes the refracted ray to go parallel to the surface, perpendicular to the normal line. So we see this as demonstrated with the green ray of light there. So how can we find the critical angle using Snell's law? Well, the critical angle is theta 1, okay, and the theta 2 we always again measure from the normal line is 90 degrees. It's going parallel to the surface, but it's perpendicular to the normal line. So using Snell's law, we find that theta 1 again is critical angle, theta 2 is 90 degrees, and so we would set it up this way and we could calculate the critical angle. Okay. So what happens when there's total internal reflection? This is where the incident ray cannot leave the first medium because the critical angle was exceeded. So the incident ray is greater than the critical angle, and so all of that light bounces back in totally internally reflected. Okay, there's two requirements for that. One, that the incident ray is greater than the critical angle, which is demonstrated here in the purple. And then the second thing you find is that light has to go from a higher index of refraction to a lower index of refraction. If we look at this and if we take the scenario of like going from a low index of refraction to a high index of refraction where the ray of light bends towards the normal line, if we increase that angle of incidence, we are increasing the angle of refraction, but there's never a point where that refracted ray is going to go parallel to the surface because it's always bending towards the normal line, not away. So a whole nother topic is dispersion. Dispersion happens when white light is separated into the color spectrum due to refraction. And so we have a prism here. Let's say it's made out of glass. We're going to pass white light into it, and at a certain angle, you get a rainbow coming out. So this is the white light's being separated out into the color spectrum, and the reason this happens is shorter wavelengths of light travel slower through the material than longer wavelengths, therefore causing the shorter wavelengths to refract or bend more because they're affected more by that material. So which color has the least angle of deviation? Red, because it has the longest wavelength, and purple has the greatest angle of deviation because it has the shortest wavelength. So there you go.